Welcome, curious minds, to the deep dive. Imagine, for a moment, being able to tune in to the subtle electrical whispers of your own brain.
Yeah, like listening in on its secret conversations.
Exactly. What if you could go on a scientific treasure hunt, not for gold, but for the incredible secrets hidden right there, inside those whispers? That's pretty much our adventure today. So our mission for this deep dive is to take this stack of technical notes we've gathered. It feels almost like a forensic report from a data scientist, actually.
It kind of does, yeah.
And pull out the most fascinating nuggets of knowledge. We're going to walk you through the path, which, let me tell you, can be pretty tricky, from raw, complex brain data to actually understanding something meaningful.
And there were definitely some surprises.
Oh, yeah. Puzzles, roadblocks, the works. Think of it as a real behind-the-scenes look at how scientists turn those, squiggly lines into actual insights.
And our source material for today's exploration, it comes from this collaborative dive we did into publicly available EEG data, specifically from a fantastic resource called PhysioNet.
PhysioNet, right.
And we've been using some pretty powerful tools, Python libraries like MNE-Python and WFDB. This dive really shows how the pros try to extract knowledge from these incredibly complex data sets, warts and all.
Okay, let's unpack this then. Jump right into the brain's data trails. We're talking about electroencephalogram, or EEG, data. For anyone maybe new to this, what is EEG data, fundamentally?
Right. So at its core, EEG data is raw electrophysiological information. Imagine placing tiny sensors, these electrodes, on someone's scalp.
Okay.
These sensors pick up the incredibly faint electrical signals that the brain produces as neurons communicate with each other.
Wow, super faint.
Yeah, tiny voltages. And it's a continuous recording of that electrical activity. So it's like a direct, real-time window into what the brain is doing moment by moment.
A window into the brain. And where did we find this particular treasure trove of brain signals?
So our journey started on PhysioNet, which, as I mentioned, is just this amazing public resource for medical and scientific data. It's a huge open library, but specifically for biological signals.
Like heartbeats, brain waves, that sort of thing.
Exactly. And our specific quest began within a database there called EEG. We were looking for data from one particular person, subject S014.
Okay, subject S014, got it. So we're on the hunt. What were the first big finds when we started, digging into their directory?
Well, the initial success came pretty quickly, actually. We found and listed these records, specifically files ending in DIDF, that's the European data format.
Ah, EDF.
Yeah. Within the S014 directory, we saw, for instance, a file named S014R02.edf.
And that EDF file, that's the main thing, right? The core data file containing all those continuous EEG recordings.
That's exactly right. It holds all those squiggly lines representing brain activity over time. But here's where it gets really interesting, and where our little detective story began. Alongside these EDF files, we found these companion files. They had the same name, but with a .event extension added on, like S012 or 2.edf.event.
.event. Okay, the plot thickens. What are these mysterious .event files supposed to do? They sound important.
Oh, they are absolutely crucial, or they should be. These .event files are meant to hold what we call event markers.
Event markers.
Think of them like digital timestamps. They synchronize the continuous EEG data with specific things that happen during the recording.
Like what kind of things?
Well, for example, if the subject was asked to open or close their eyes, or maybe they saw a flashing light or pressed a button, an event marker would note the precise moment that happened in the EEG data.
Ah, okay.
Without these markers, you just have a whole lot of electrical activity, but no context. You wouldn't know what the brain was doing when.
Right, you just see the squiggles change, but not know why. That makes sense. So, okay, we found the core EEG data in the EDF file. The next logical step would be to actually load this brain data into our analysis tools, right? Did that first attempt go smoothly? Opening the evidence bag, so to speak.
Yeah. Thankfully, loading the main S014R02.edf file itself, that went fine. We used MNE-Python.
MNE-Python. Remind us what that is.
It's a specialized open source library, really popular in neuroscience. It's specifically designed for analyzing human neurophysiological data like EEG, MEG, that kind of stuff.
Gotcha.
So loading the EDF into MNE-Python was a success. And that was a major step, getting the raw data out of its storage format and into a structure we could actually work with.
Okay, great. And once it was loaded, what did we learn just from that initial look? Like, what kind of info does the raw data file itself tell us?
We learned quite a bit just from inspecting the header information. That's basically the metadata embedded within the file.
Like the file's ID card.
Exactly. MNE-Python makes it pretty easy to access. We could see critical details like the number of channels, that's how many electrodes were on the subject's scalp, in this case 64,
64 sensors, okay.
and the sampling frequency. That tells us how many data points per second were recorded for each channel. Important stuff for understanding the quality and scope of the data. It's like getting the basic map of our brain signals.
All right, so far so good. We've got the EEG data loaded. We know the basics. 64 channels, how fast it was recorded. But now comes the part that really turned into a bit of a data science detective story.
Yeah.
The curious case of the unreadable event files. After loading the EDF, what was that critical next step, and what was the roadblock we hit?
Well, the critical next step was simple.
Yeah.
Read that S013R02.eds.event file. We needed those event markers to make sense of the EEG.
Right, for the context.
Exactly. But the roadblock was immediate. Just trying to read that .event file, bam, Unicode decode error.
A Unicode decode error. Okay, that sounds like the computer just threw its hands up. For someone like me, not deep in coding, what does that actually mean when you hit that with real data?
That's a really good question because that happens all the time in data science. It basically means the computer tried to interpret the file's raw bytes, the ones and zeros, as if it were human-readable text, like a standard document.
Okay.
But it couldn't understand the file's language, its encoding. It was expecting something common, maybe like UTF-8, but the file clearly wasn't written in that code.
So it's like trying to read a book written in an alphabet you don't recognize.
Exactly that. The computer knows it's supposed to be text, but the symbols don't make sense in the way it expects.
Okay, so how did you try to fix that? Was there an aha moment, maybe trying a different alphabet?
There was an aha for solving that specific error, yeah. But it immediately led to a deeper, much more frustrating mystery. We tried a common fix. We told the computer, okay, try reading it using Latin 1 encoding instead. It's another way of interpreting bytes.
And did that work?
Well, it solved the Unicode decode error. The program didn't crash anymore. It could technically read the bytes. But then the real puzzle was revealed.
Which was?
The file's content, even when read with Latin 1, was just not human-readable text. It was mostly gibberish, weird symbols.
What did it actually look like? Can you describe it?
It was mostly unprintable characters, but right in the middle of this binary mess, we saw this little snippet of actual text. XG hashtag time resolution, 160 II.
Whoa, time resolution, 160. That looks like a clue.
Exactly. That little string embedded in the chaos was the big realization. This wasn't a simple text log file we can just open and read line by line. It had some specific, unknown, non-standard binary format.
Binary meaning computer code, not text.
Good. To parse it correctly, to pull out those event timings, we needed to understand its exact structure, its layout, which meant we needed to find documentation for it. And that kicked off a real data science treasure hunt.
So you knew you needed the instruction manual for this weird file format. What did you try next to find clues? Where do you even look for something like that?
Well, we tried a few things available right there on PhysioNet.
All right.
We checked a file called sh256scms.txt.
What's that for?
It's mainly for verifying file integrity, making sure your download isn't corrupted. Useful, but unfortunately it offered zero clues about the .event files format.
Okay, dead end there.
Yep. Then we tried using another tool from the WFFDB library, a function called getRecordList, hoping it might programmatically list all the associated files, including the .event ones, maybe giving us a hint.
Yeah.
Mostly it just listed the primary EDF files. Again, it sort of added to the mystery, really. How are these event files officially linked or accessed within the database structure if the tools don't easily see them? It felt like we were looking for a key, but the keyholes kept disappearing.
Frustrating. And you even hit another little snag, a classic data science quirk with the different function, wfdb.ard header, right? Tell us about that.
Oh, absolutely. And this wasn't even about the event files. This was just trying to read the header of the EDF file using a different library, WFDB. It turns out when using wfdb.ard header locally on an EDF file, it unexpectedly also required a separate .heo file.
A different header file, even though the info is inside the EDF.
Exactly. MNE-Python didn't need it, but WFDB did for the same task. It's a small thing, but it's a perfect example of how even standard tools can have their own specific requirements and quirks. You assume one tool works one way, another expects something slightly different. It just adds another layer to the detective work.
It really shows you have to know your tools inside and out. So, faced with this persistent .event file mystery for subject S014, What was the next logical step in your investigation? Did you, try another subject?
Exactly right. That was
Yeah.
the next thought. Maybe S0V14 was just weird.
We decided to expand the search and look at another subject, subject A001, to see if this .event file issue was consistent across the database or just a one-off fluke.
Makes sense. And what did you find with subject S001? Same problem. Pretty much, yeah. We checked the directory listing for S001, and sure enough, we saw the same pattern. S001R01.edf paired with S001R01.edf.event and S0001002.edf.event. So these pairs seem standard for this data set.
Okay, so the structure is consistent.
Right. So we downloaded S00001R02.edf and its corresponding S001R02.eds.event file. Loading the EDF file, S001R02.edf into MNE, no problem. Worked just like S0 4 times.
But the event file.
But the event file? Same story. We tried reading S001R02.edf.event, specifically reading it in binary mode this time, just to see the raw bytes directly.
And what did the raw bytes look like?
It was this sequence.
Yeah.
Hashtag time resolution, 160. Right there in the middle of all that binary code stuff.
Yep, embedded right in the raw bytes. It's a unique clue, definitely, a potential search term if you were digging through documentation.
So it sounds like you had a fingerprint, but still no clear instructions on how to read the rest of the message. Precisely. It strongly suggests some kind of structured binary data with embedded metadata, but the problem was our automated process, the script we were running, couldn't just go off and search external websites like PhysioNet's documentation pages or Google for that string.
Ah, right. The code can't do the human part of the detective work.
Exactly. It highlights that even with all these powerful tools, sometimes that crucial step requires manual intervention, taking that unique string hashtag time resolution 160 and actually searching for documentation, forum posts, anything that mentions it. That's the human detective work still needed to crack the code.
It's like finding a single cryptic note in a treasure chest and realizing you need to go back to the library or maybe ask an old professor to figure out what language it's even written in.
That's a great analogy.
It's a fantastic reminder, isn't it?
Yeah.
Data science isn't just algorithms running. It's about persistent human curiosity. Okay, let's shift gears slightly. While that event file remains our unsolved puzzle for now, a key piece of the treasure was already in our grasp. The raw EEG data itself from the EDF file.
Right, the data we could read.
Exactly. So what did we discover once we successfully loaded that primary EDF file from subject S010, SRI1FRR02.edf, and actually got to see the brain's whispers in action?
Well, we shifted our focus to visualization. This is where it gets really cool, I think, where those electrical whispers truly become visible. We were able to plot the time series for multiple channels simultaneously.
So you actually see the squiggly lines.
You actually see the squiggly lines, rows and rows of them, each representing one electrode on the scalp, showing its voltage changing over time. It's quite captivating, honestly, like watching a complex rhythmic heartbeat, but, for the brain.
Yeah.
You can literally observe the brain's baseline activity, its natural rhythms, how they fluctuate.
That sounds amazing. And you mentioned you had an image, 64-channel charbro.png, which shows where all 64 electrodes are placed on the scalp. How do you go from just seeing those lines to actually mapping the activity onto a head shape like that?
Yeah, that image is an electrode placement map. It's crucial because it tells us where each squiggly line is coming from on the scalp. Now, directly overlaying our plot onto that specific PNG image, that's technically complex and not really a standard scientific visualization.
Okay, so not drag and drop.
No, not quite. But
Yeah.
MNE-Python offers much more powerful built-in visualizations that are directly related to electrode placement.
Everything we do is available freely on bionichaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.